Hello there everyone, thank you for joining me today as we discuss U-Substitution, a technique that will help us to evaluate integrals of compositions of functions. So, as I previously mentioned, this technique of U-Substitution is a technique that helps us to find antiderivatives of compositions of functions. There's a series of steps we can follow here. You can pause, read them, write them down if you like. I like to approach it from a very mechanical perspective where we're able to make direct substitutions and we get some nice canceling action to happen, which helps the antiderivative become a little bit easier to find. So the steps are here. You can read them through to keep this video as brief as possible. I'm not going to read through every single step, but I will illustrate the concept using the example down below. So we have the indefinite integral of x squared plus 1 squared times 2x dx. We've got a composition of functions here. We have x squared plus 1 composed with the squaring function, and we even have the product of 2x on the outside of that. Well, recall from the first part of this course that when we differentiate compositions of functions, we need that chain rule. So here we're kind of doing the chain rule in reverse, finding an antiderivative, okay? The thought is that we make a U-substitution. We let U equal part of our integrand, and then we proceed accordingly to try to make some direct substitutions, making this antiderivative easier to find. Now, as it says here, usually it's best to make your U-substitution for the inside part of the composition. Something that's raised to a power, something that's inside a square root, something that's inside a trig function. Here, x squared plus 1 is being raised to a power, so I'm going to make my U-substitution accordingly. I'm going to let U equal x squared plus 1. Now, when we find antiderivatives, if I'm going to make a U-substitution and I have U in here, we need our variable of integration to be the same. We need a du. So the thought here is that we take our U-substitution and we calculate what du dx would be, what the derivative of u is with respect to x. Like back when we did that implicit differentiation in the first part of this course. Well, if I differentiate x squared plus 1 with respect to x, we get 2x. Okay? And this is now where the way I approach it starts to veer off from how other people might approach it. Whenever possible, I want to make this as easy as possible to make direct substitutions here. So I don't see a du dx in this at all, but I do see a dx right here. So if I can take what I have in red and solve for dx, then I'll be able to make a direct substitution. And if I solve for dx, this is what I get. So now I can go over to my indefinite integral here and make some direct substitutions. Everything here is what we're letting u equal. So right here we have u squared. We got this 2x for the moment, but when I sub in everything that dx equals now, dx is equal to du over 2x. You'll notice that these 2x's cancel out, and all we have left then is the indefinite integral of u squared du. Well, finding an antiderivative for u squared isn't that difficult. We add 1 to the exponent and divide by the new exponent, keeping in mind we've got to add that constant at the end. There could be some constant at the end of all this. The last step here is to resubstitute so I have my final answer in terms of x again. Well, remember what u equaled. U was equal to x squared plus 1. So if we have 1/3 of u cubed, we have 1/3 of x squared plus 1 cubed, and we have that plus c at the end. That last step is just substituting all of this stuff back in for u. That's all it is. You could check this answer by differentiation, just like you always could when evaluating indefinite integrals. So that right there is an example of U-substitution. Okay. Now, again, to try to keep this video a little bit more brief, we're going to skip this example because it's similar to the last one, but let's try something with a square root in it. So zooming in here for a moment, we have the indefinite integral of t cubed times the square root of t to the 4th plus 5. Let's decide what our u substitution should be first. The tip is to let u equal the innermost part of a composition, something inside of a root, something inside of a power, something inside of a trig function, here t to the 4th plus 5. So now we calculate the derivative of u with respect to t, and that would be 4t cubed. Remember, the thought is to now solve for dt, so we can make a direct substitution for that. And if you take this equation and solve for dt, this is what you'll get. So let's go over here now and let's make our substitutions. We've got the indefinite integral, and I'll have my t cubed for the moment. This is the square root of u, and I'm going to write that using exponents so I can find an antiderivative easier when the time comes. And for dt, we will substitute in everything that dt equals. Well, notice here again we get our t cubes to cancel, but nothing cancels with that 4 in the denominator. So what I'm going to do, since that's a 4 in the denominator, I'm going to factor 1/4 out of my indefinite integral, just making it a little bit easier for me to find my antiderivative. Well, to find an antiderivative, we add 1 to the exponent and divide by the new exponent. If we add 1 to the new exponent, we'd get u to the power of 3/2. If we divide by that exponent, we'd be dividing by 3/2, which is the same thing as multiplying by 2/3. Well, 1/4 times 2/3, that's what? 2/12, that's 1/6. So I got a 1/6 right here. We've got u to the power of 3/2, but I'm going to make that substitution back. I'm going to plug back in everything that u is equal to. And there we have our antiderivative. Let's try this example here. Here we have a rational expression of sorts. Again, the thought is to let u equal the innermost part of a composition, like something raised to a power, in this case 1 plus x to the 4th. So then we calculate the derivative of u with respect to x, which would be 4x cubed. I like to then solve for dx so I can make a direct substitution on that. And this is what we'll get when we solve for dx. So switching colors now, we've got the indefinite integral. We got this x cubed. This would be u to the power of -2 right here. And for dx, we are subbing in everything that dx is equal to. Here again, we get these x cubes to cancel, but that 4 in the denominator does not. So like I did before, I'll factor 1/4 out, making my antiderivative a little bit more clear. We're going to have to add 1 to the exponent and divide by that new exponent. So we have, and I'm going to put a -1 here to take care of that negative. The 4 is in the denominator. That u has a negative exponent, so that's going to end up in the denominator down here, and then plus c. Let's try an example with trig elements here. Let's set up our U-substitution. Usually helpful to try letting u equal something that's inside of a root, inside of a power, inside of a trig function. In this case, let's try letting u equal tangent of x. Then the derivative of u with respect to x. Well, the derivative of tangent is secant squared. Here again, let's solve for dx so we can make that direct substitution. Okay, I'm talking here. So switching colors now, we have the indefinite integral. Let's see, this is the square root of u. So we'll call u to the power of 1/2. That secant squared x is there, but when we sub in for dx, we can see how that secant squared x is going to go away. So we have the indefinite integral of u to the power of 1/2 du. So we find an antiderivative here. We add 1 to the exponent and divide by the new exponent. Again, dividing by 3/2 is the same thing as multiplying by 2/3. Resubstituting back in, we have 2/3. This would be tangent of x to the power of 3/2 plus c. So there we have done now a total of 4 examples of evaluating indefinite integrals using U-substitution. This is a new technique that requires practice and repetition, and that's what our homework is for. Now, it is possible to evaluate definite integrals using U-substitution as well. And we kind of have 2 choices about how we want to handle these definite integrals. And I've got the same problem twice so I can show you the difference between those 2 choices. Now, those 2 choices will start off the same, though. We still need to figure out what we're going to let u equal and proceed from there. So here, using our thought process, it'd be helpful to try letting u equal x squared plus 1. Then the derivative of u with respect to x would be 2x, and like you've seen, I like to then solve for dx directly so I can make a direct substitution. Switching colors, got our x here. This would be u cubed, and then for dx, we sub in what dx is equal to. We'll get our x's to cancel. That 1/2 does not, though, so I'll factor it out in front, leaving us with this much. We now find an antiderivative for u cubed. That would be u to the fourth over 4. And remember, with definite integrals, we do not add that plus c, because when we go through the process of evaluating and doing our subtraction step, they would cancel out anyway. So we have here, I guess, 1/8 u to the fourth here. Now, you'll notice that I have neglected to copy down my bounds of integration on each of those steps, and I've hesitated to do that because that's where the difference in our two choices lie. Okay, the first part of this will be the same regardless of which choice we take. We define what u is equal to, we make our U-substitution, we get that antiderivative, we get to where I'm at right now. But then this is where things start to deviate a little bit. So I'm going to bring this over here. Right now we found our antiderivative. We've got 1/8 u to the fourth, okay? And we're ready to start evaluating that. Well, two choices here. Choice number 1 is to resubstitute back in what u equals like we did so far in our lesson. And if I do that, and I'll factor the 1/8 out to make this a little bit easier, if I resubstitute what u is equal to x squared plus 1, and our antiderivative found that to the fourth power. And if I resubstitute what u is equal to in terms of x, I can use those same limits of integration that we had at the beginning of this problem, 0 and 1. And now if I go through the process of running these numbers, I'll have 1/8, okay, and then 1 squared plus 1 to the fourth. That's like capital F of B in that fundamental theorem of calculus definition, minus that capital F of A, I guess 0 squared plus 1 to the fourth. This is 1/8, and let's see, that would be 2 in there. 2 to the fourth is 16. This would be 1. 1 to the fourth is 1. This would be 1/8 of 15. Call it 15/8. We could confirm that using that feature of our graphing calculator, remember. Check our answer that way. Okay, so there is one of our choices to resubstitute what u is equal to in terms of x, and then use the original limits of integration. Wasn't too terribly difficult to do here because u was not equal to anything that was too terribly difficult, and our antiderivative wasn't that difficult. However, choice number 2 you might like more, because in choice number 2 we can leave it as 1/8 u to the fourth. And you know, like I talked about, I could factor that 1/8 out to make this a little bit easier. But if I want to leave it in terms of u, I've got to recalculate what our limits of integration are in terms of u. So, going back to what we let u equal, remember we let u equal x squared plus 1, let's figure out what our new limits are equal to in terms of u. In other words, let's plug 1 into that function u, and let's plug 0 into that function u and see what we get. When I talk about that function u, I'm talking about x squared plus 1. Well, then 1 squared plus 1, 0 squared plus 1. This is 2, this is 1. So then we're going to evaluate this not from 0 to 1, but if I'm going to keep this in terms of u, we're going to evaluate this from x equals 1 to x equals 2. Well, that's 1/8. Let's see, 2 to the fourth minus 1 to the fourth. And you'll notice that here again we get our 16 minus 1 in here, giving us the final answer of 15/8. So, when we evaluate definite integrals using U-substitution, we have two choices. We can go through our U-sub process, then when it comes time to evaluate our antiderivative, we can resubstitute our expression for x and use the original limits of integration, or recalculate our limits of integration using u and use those instead. I prefer this choice almost all of the time, so when you check my answer keys, you are more likely to see that. There is a case to be made for this, when our U-substitution is not very complicated perhaps, but most of the time I'm going to use choice number 2. So today we learned about U-substitution and how we can use it to evaluate indefinite integrals and definite integrals when that integrand is a composition of functions. Thank you for watching.